downwards. So if you look at the scattering cross-section of a spherical particle, it goes as omega 4, and then it goes up, and then eventually it saturates. When you go to very high frequency, what is the saturation constant? What is that cross-section of it? This is me scattering, okay? This is what we call me scattering. A lot of people know how to write me series codes and look for me scattering solution. Those are good for all frequencies. But what is the asymptote? It will asymptote to. Yes?
Pi a squared.
Pi a squared. Do you know why?
It is like a disk.
You will start to have a scattering cross-section of a disk because you are reaching the regime of optical physics. Okay, you are reaching the regime of optical physics. And that sphere will cast a shadow. If you have this thing and you shine light on it, and then it will cast a shadow. Behind it, it will cast a shadow. The shadow has an area of pi a squared behind. And you will learn from the optical theorem that you need only to know the forward scattering amplitude of a particle. You know the scattered energy everywhere. And this follows from the optical theorem. And this is somewhat related to the optical theorem, which you are asked to prove by reading Jackson and then go to the proof and tell me the physical meaning of what optical theorem is. Okay. And then maybe with the understanding of the optical theorem, you understand radar cross-sections better. Okay? So that will be a good exercise for you. Any questions regarding?
But the cloud is white. I suppose there are a lot of water balls.
Yeah, they're larger. They're larger water molecules in the cloud, denser. So when they are larger and denser, I suppose they also scatter lower frequency light, not just high frequency light. And that's why the cloud appears white. Okay, things are very complicated, and people might ask, why doesn't the sky look purple or something, right? Because ultraviolet is higher frequencies than blue, right? So if you go with this logic, then more and more high frequency light will be scattered. But then you can say, because of Rayleigh scattering, it has to come down. And I think the solar spectrum is such that there's not so much ultraviolet light anyhow. There are UV lights in sun ray. You have to protect yourself. Wear sunscreen when you go out because they're not supposed to be good for your skin. So if you go out in the sun, wear a lot of sunscreen, protect yourself from UV radiation. But it's not as much as it will turn the sky purple or violet or something. Or because of Rayleigh scattering too. There's a peak to all this scattering. Okay. Yes? Oh yeah, the atmosphere protects us from UV as well, from UV light. So if you live in high altitude, like the Himalayas or Tibet or some high country, then you have to protect yourself more. Okay, you have to protect yourself more. It's very strange if you go and visit people in high country. They are less sensitive to color. And they tend to paint very, very brilliant color. They're not like people who stay in the lowland when they paint. The painting have a different mixture of color. Okay, because they live in the highland, their eyes are blinded to a certain color, so they have to paint with very brilliant color. You can see that from their art. Right? So the last topic that I'd like to talk on is actually surface enhanced Raman scattering. This is actually quite a popular technique to probe molecules in the spectroscopy of molecules. And how this comes about is because Raman scattering is the fact that if you shine light onto an atom, the light can get absorbed and it can radiate. Usually if you follow the Fermi golden rule, the light comes in with omega naught, it will also radiate with omega naught. Okay? And this can be due to absorption and emission by the transition of energy level in the atom. But what happens if this atom is more complicated? Say it's a molecule. Say if it's H2O, I don't know if H2O has Raman scattering or not, but if you have a molecule, the physics is rather complicated because the molecule can vibrate also. It can vibrate due to a number of things. It can vibrate due to thermal vibration. Because it's vibrating, it actually modulates the scattered field. It's like modulated scattering. There's actually a field in microwave engineering called modulated scattering. So if this thing is vibrating at another frequency, say omega r, okay, the molecule is vibrating at another frequency, omega r. It's like a mixer that you have in a microwave circuit. If your mixer, if it's an oscillator, it's oscillating omega naught, if you vibrate the mixer, if in another frequency, you have mixture of frequencies, so the scattered field can have this kind of effect. It can either have a plus or minus effect. Okay, you know that when you mix two things together, like sine omega RT, sine omega naught T. So due to any nonlinear effect, you have this kind of multiplication. You multiply instead of adding two signals together. This is nonlinearity, and then if you work this out, then you will have four terms, right? 1/4 to the I omega R plus omega naught T plus T to the minus I omega R plus omega naught T, and then there will be the mixed forms. You have four terms like this, I believe. And then you can see that they have different frequencies. Some of them are higher, some of them are lower when you have nonlinearity. Nonlinearity will exist in systems like that. And it's called Raman scattering. It was discovered by Chandrasekhar Raman, right? Am I right? Aditya will know his full name. Chandrasekhar Raman something. Raman, right? What is his full name? Chandrasekhar Venkat Raman. Okay, very long. Chandrasekhar Venkat Raman. What year was that, Aditya? What year was it?
Can you want the Nobel?
No, what year did he discover this phenomenon?
1920.
1920? Yeah, quite long ago. Okay. 1920. So this becomes something notable, something important, because you can use that to study the spectroscopy of molecules. And if the molecule is stuck to another molecule, the Raman scattering spectrum will change. So it's used to study trace elements. When you put trace elements through very complicated things, if you see a shift in the scattering frequency, it's due to the presence of other things. It's used a lot in optical spectroscopy these days. So what causes enhancement then? It turns out that you can use nanoparticles and rough surfaces to enhance Raman scattering. We see that if you have a nanoparticle, if the nanoparticle resonates, the field around the nanoparticle can become very strong. And hence use to enhance this kind of optical absorption and emission effect. Okay, another place where they have seen enhanced Raman scattering is actually in rough surfaces. Somehow if they put molecules on rough surfaces, the Raman spectrum becomes more enhanced. Or maybe due to sharp corners. They don't really know why. Okay, maybe if this molecule gets stuck to places where the electric field is very strong, they find that things are enhanced, or they found that if you have nanoparticles and if there are molecules stuck in between those nanoparticles, you tend to get enhancement of this Raman scattering. So roughly, they find enhancement on the order of 10,000 times or something like that, okay, depending on the experimental setting. So you can roughly explain the effect in this manner, that say if the dipole moment of a molecule is proportional to its polarizability, okay, then that the dipole moment is usually the product of two frequencies. The polarizability might have a vibrating frequency of omega r, and then the exciting field might have a different frequency, omega. Okay, omega. So you can explain it with a very simplistic model like this, that the polarizability, the dipole thing itself, depending on how it's polarized, also depends on the vibrational frequency of the molecule. And then the optical signal coming in will have two terms, the incident field and the scattered field. The scattered field can be very, very strong in some occasions. So because of the product of these two, when you multiply two things, you get plus and minus frequencies. Those are called Stokes and anti-Stokes frequencies. Stokes and anti-Stokes. Frequencies, because you have things that you have this dominant frequency, you might get some frequency higher, some frequencies that are lower. One is called a Stokes phenomenon, the other one is called an anti-Stokes phenomenon. And then you can explain the enhancement by the fact that this scattered field, okay, this scattered field can be much, much larger than the incident field by a factor of 100 or 1,000 or so. So when you square this thing, which is what intensity is proportional to, you get a huge factor in the enhanced field. Okay, because of that. That essentially is the physics behind it. Okay, other than the fact that you can do the complicated mathematics. So they have these things that they say. Okay, you read up on the detail on Novotny. They say the enhancement effect is 1 over F2 omega r plus 1 over F1 omega, which is the incident frequency. Okay, and then the enhancement is due to the product of these two. This is the enhancement of the polarizability, because the polarizability can see a very strong field. And this is the enhancement of the scattered field that's come in because the scattered field itself also get enhanced. This has the same frequency. And this factor can also be enhanced by some other thing. Okay, so if you take into account of this, then you can have enhancement as F1 times F2 squared. And that's why you see this enhancement. This is just a proposed explanation for it. A proposed explanation as to why you see all this enhancement. Nobody really knows why. This is just a proposition. That's why they have this effect. So you often will hear about this, the use of this technique in optics, in nano-optics these days, because you can make nanostructures and put molecules next to them. You can make optical grading, you can make photonic crystals. You put molecules next to them, you will see enhanced Raman scattering. Okay, yes?
So isn't it the idea of Raman scattering is like when you, the incident, the scattered wave, if
Right.
it's, I think if it's Stokes, it takes part of the energy of the vibrational energy of the molecule.
Okay.
It goes to a lower state, so is that where the extra intensity coming from?
No, it wouldn't be that big, you see. That taking energy from the vibrational energy of the molecule will be extremely small amount of energy. Okay, this molecule has some energy there. It's vibrating. But what matters the most is the fact that if you put these molecules next to a nanoparticle, you have an incident field that comes in, that excites it. But then you can also have a field that bounces off the other one that is enhanced by the particle next to it. So it receives an incident field that is much, much stronger. So it receives an incident field that is much, much stronger than the particle by itself. And this F1 omega is due to the enhancement by the nanoparticle. And then if it comes up with a different frequency, say if this particle now radiates in a different frequency, okay, it radiates with omega r, say, which is a different frequency from omega naught. Okay, omega r would also be enhanced by this factor. Say if it's next to a nanoparticle, it will get doubly enhanced too. So omega r is also enhanced. So the Stokes frequency is also enhanced, the incident frequency is also enhanced. So it's doubly enhanced. And then you have this kind of phenomenon. Okay. It by itself, I think what you say is quantum mechanically correct, that this will have vibrational states and this will have vibrational states, and each molecule and each atom also has this optical absorption level, and if you shine light on it, those vibrational energy will be taken away, you will go to a different vibrational state. Okay, but those energy is very small. Those only small effects like this. Okay, know these two terms. So, but because of the enhancement, you have the enhancement of the Raman spectrum, as well as the incident spectrum. Okay, and then you see this big effect, which is proportional to that.
Bruce,
Yes.
well, based on your explanation, the usual scattering field should also be enhanced.
The what?
The scattering field without the addition of the just the scattering of the whole molecule
Right.
itself should also be enhanced.
No, the Raman scattering effect was first observed without enhancement, just by itself. If this molecule, if you look for it, you see a shift. You see some up and down shift. Those are very small effects. The cross section of those is 10 to the minus 16 centimeters squared. Okay, so it's extremely small effect. Okay, it's very hard to observe. It was first observed by Chandrasekhar Raman in 1920, I suppose, which is kind of phenomenal. But I think 10, 20 years later, somebody figured out a way to enhance it and see a much bigger return. And then more recently with nanotechnology and nanofabrication, it becomes a very popular thing to do. You can make nanoparticles and nanotechnology and put molecules next to that. For instance, you might use this kind of technology to, I was told by a professor Cunningham, to detect blood cancer. Say if you have one blood cancer, one of your blood molecule is different, we have a different spectroscopic signature. It might be 1 in 100 or 1 in 1,000 blood cell that behaves that way, but if you put it on the photonic crystal together with some other things, and then you tag them with nanoparticles and so on, and then you can detect all these blood samples, blood molecules that are corrupted due to cancer. So it becomes a very popular tool in diagnostic purposes in optics. Okay. Are there any questions? If not, we take a 5-minute break and then we come back. Okay?
请问你的